Hello everyone, this is Yigit Hergul. I'm a second year PhD student at the Department of Mechanical Science and Engineering under the supervision of Varda FH and in the University of Illinois Urbana-Champaign. And today we will be talking about a constrained circle packing algorithm that we are developing for path planning in growth printing. Growth printing is actually a new additive manufacturing technology using the polymers. And we are trying to create a path planning for this manufacturing technology because it requires certain constraints on the system. So the way to do this path planning is to create a circle packing, solving a circle packing problem which is very constrained, so that we are developing an algorithm, not strictly restricted to growth printing, but very useful for this application. As a motivation, different manufacturing processes require different requirements. For example, in an assembly line, the fast pace of the robots is important so that the collision becomes the main concern. For example, for a CNC, you shouldn't dive deep into the material so that you should care about this part. But for a 3D printing, you should complete the path as fast as possible. Whereas in additive manufacturing, in welding, you should also consider the heat dissipation. So new method will require a new strategy in path planning, and if you would like to just work on this novel additive manufacturing technology, we should definitely come up with a new way of path planning. So let's talk about what is this growth printing. To understand the growth printing, we should first consider the frontal polymerization, which is actually a chemical reaction. In this chemical reaction, where we have monomer liquid material, which will be converted to a solid polymer material by supplying some heat. After reaching to a certain temperature, we will initiate the first reaction of the exothermic reaction, and this will also initiate the next row so that it will be creating this solid polymer through the structure. And you can see here, when you reach to a certain temperature, you will be having this solid polymer going into the liquid monomer in your liquid bath. You can see there's this radial growth, and you can also see the bottom view of another experiment which is conducted by Young-Sung, our experimentalist collaborator. So you can see here the radial growth after the initiation. This looks like a circle in 2D since we are looking from the bottom view, but if we will move on to a 3D view, we will have a sphere since this is happening at the surface of the liquid bath. And if we can just create two of the same initiations at the same time, they will seamlessly merge. If we can do this at different locations on a 3D volume, we can just come up with any shape that we like. So this comes to sphere packing, actually, which has been studied for centuries by mathematicians and physicists. But this is still a very complex problem, especially considering the growth printing that we are trying to deal with, so that we need to just come up with a reduced version. Let's reduce the problem to a 2D so that we are currently dealing with the circle packing. In this experiment, we are again at the bottom view. You can see that we are initiating different points at the same time so that we are having the same radius at different points. And if we will have a better flexibility in manufacturing those circles, we will have more circles and we will have different radii for these circles so that we could be able to just create a better circle packing. And the way to attain this flexibility is to use lasers, actually. The only thing we need is to supply some heat to a certain point so that we can reach up to a certain temperature. So this can be done by lasers. And this study shows that different locations can be initiated at the same time and they will merge, as you'll predict. So we need to come up with a solution. We need to come up with an algorithm which will require these conditions to satisfy. One of the most important one is the flexibility of printable shapes. So you should be able to just create circle packing for any shape that you like to create, because this is the purpose of additive manufacturing. And there is this sufficient accuracy of object because you want your object that you're manufacturing to look like the design that you have done. The printing time is also very important, so that we needed to come up with a basic shape which will create some challenges for us. So triangle is a good shape because it is a basic shape, but in the same time it has corners and acute angles so that it is challenging enough to deal with. So since we have just set the geometry of the problem, let's move on to the process parameters. In process parameters, we have 4 very important process parameters: the front speed, the velocity of propagation of your front when you start the initiation, dwell time, the amount of time required to initiate this first reaction in your liquid bath, number of initiators, number of lasers that you have, how many points that you can initiate at the same time, and characteristic length, what is the length of the triangle that you want to create. So in here you can see different colors. In red, this means that we have these knobs that we turn. If we just decrease the values of these knobs, this means that we will have a better circle packing when we decrease them. So red indicates this one. And the green colors indicates that if you increase these parameters, you will have a better circle packing. So the two will significantly improve the circle packing that you have. The negative ones are the ones that we will look into because we are engineers and we like solving negative things. Let's look on this single initiator example. Assume we have only one laser that we can shine at some point, and we have this nice liquid bath. At time 0, let's shine our lasers to a point in this liquid bath where we have monomers. And after some time TD, when time is equal to TD, we will be able to initiate the first reaction at the first point. And let's assume that we just shine our laser to another point instantaneously, so that whenever we initiate the first point, we directly move onto the second point and direct our laser so that we are supplying heat to this point at time TD. And after same time, another TD, we have T is equal to 2D right now. The first circle, surprise, surprise, has grown. And the second one has initiated because you have reached to a certain temperature there. And then let's instantaneously shine our laser to another point. This is a simplification that we are doing. And here you can see at time 3D, we have grown circles at different sizes, and the third one has initiated. Let's make them grow a little bit more. We will have discrete sizes for these circles. And we are assuming that the front velocity that we're having is constant for each one. Whenever you initiate it, it will grow with this constant velocity. And considering this, we can come up with a new parameter, radius difference, which is actually defined as the multiplication of the front speed and the dwell time in our process parameters. So what does this mean is that you will have delta R increase in your radius of your circle if you wait TD amount of time. So you're actually allowing your previous circles to grow at a velocity of front speed to a time of dwell time, so that this is the radius incline that you're getting. Every time you're increasing the radius by delta R. So that's why when we initiate the first one and move on to the second one, during that period of time, we'll be able to increase it 1 delta R. So that's why we have delta R difference between the consecutive circles. So we have this discrete model, right? We have discrete circles. And we can actually keep doing this. We can increase the number of circles that we have, and we will have delta R difference for each one of them. And we can just come up with a toy box model where we just put a lot of circles into one box, and then we can just play around with those circles to create a nice circle packing. We can just change their locations and take different circles from the toy box depending on the application that we are doing. We can just do this randomly, like throw the circles in your toy box into a triangle or any shape that you like to have, and then apply some repulsive forces between the circles depending on their overlaps, so that we will have an expanded structure. The circles will repel each other so that we will be able to have a better circle packing. So in here, the problem with the random throwing the circles inside, we will have those little circles trapped inside. The thing is, if you will have those small circles at the sides, at the corners of this geometry, we will have a better circle packing. So this method, this random method, is actually not providing a sufficient accuracy of the object that we want to create, because we can do it better. So we need to introduce some more intentionality into this study. Let's do this by creating this largest gap algorithm. Largest gap algorithm does this. We have the geometry and we just look at the image and consider the largest gap that we have. When we have the largest gap, we go to our toy box, we see which circle we can put there, and we just put the largest circle we can put at this largest gap. And we can just keep doing this. By keep doing it, we can just create a circle packing with matching largest area with largest circles because we have a scarcity of circles. We don't have enough circles. The frontal velocity is very fast. The dwell time is very high, so that it takes a lot of time to initiate new circles, so that we have a scarcity, so that we need to make each circle count into our circle packing. So by applying potential energy minimization, again, by making the circles repel each other and optimizing the energy so that we can have a stable structure, we can create the circle packing and the simulation. So you can have a sufficient accuracy with this method, and the flexibility is actually very high because you can just circle pack a triangle, a map, or any other object that you like to pack. So let's focus on another parameter, the multiple initiation points. So Ni is the number of initiators, and you remember if you will have single initiator, we will have a toy box. If you have two initiator, what we'll have is we will have two toy box. So you can initiate the two lasers. You can just shine them at the same time and have exactly the same radii, or you can put some offset between them so that you will have a better flexibility between them, right? So, and the covered area ratio is expected to increase as we increase this number of initiators. You can see on the x-axis we have the number of initiators. On the y-axis we have the covered area ratio, which is defined as the covered area over the total area. And here you can see that we are increasing it significantly, but after some point, it doesn't matter to increase it a lot. So you need to find a sweet spot because increasing the number of initiators actually is very expensive. So let's move on to another parameter, limiting the manufacturing time. What is the thing that determines the manufacturing time in our circle packing? It is actually the first circle that you are creating. So in here you can see we have the largest possible circle that can be fitted into this structure. And once you initiate it, what's happening is you will wait for this to grow to this size, so that it will take a lot of time to manufacture this structure if you want to have this largest diameter. So manufacturing time will increase as the largest diameter in your circle packing has increased. So let's define this targeted process time that we would like to have. You want to create an object in this time, and T manufacturing time as the current manufacturing time if you are doing this circle packing. And in this case we have probably will be beyond the manufacturing time, because the main part of growth printing is actually reducing the manufacturing time, and we can further reduce by creating a nice circle packing. So in this case, we have shrink the largest diameter that we have so that we don't need to wait a lot of time for this structure to be grown. In other words, if you just initiate these points, you can just take them before so that you will have this shape instead of this. You don't need to wait a lot of time to just create the larger one, so that we can just take our structure at the time of the targeted process time, so that we can say that they're equal. So if you're not very patient, you can just take it beforehand. But in this case, yes, we are below the manufacturing time, but we didn't allow the circles to grow to a certain size so that you will be able to cover the whole shape, right? So that you don't have a good area coverage in this case. So that we need to come up with a sweet spot for this manufacturing time and the diameter limit. So we can do some optimization about this diameter limit. Here you can see we have another knob that we can play around with, another knob that we can turn, and we call it as the maximum, which is the largest diameter in our circle packing. This is not the largest diameter in your toy box. This is not the largest diameter that could be fit into the geometry. It is not that, but it is actually a variable. It is something that you can play around with and consider it as a knob. And you can just shrink this first circle or increase its diameter depending on the application that you want to have. And the maximum is actually a knob, a variable that when you decrease it a lot, you won't get a good result. And also, if you increase the D maximum a lot so that you have the largest possible diameter, then you won't get a perfect result again. So there's actually a sweet spot. You need to find a sweet spot by applying some optimization. So this can be achieved. And when we plot this figure, we have the covered area ratio in the y-axis and the D maximum over L in the y-axis. You remember the maximum is directly related to the manufacturing time. So T manufacturing increases as we increase this D maximum value, the largest diameter that we have in our circle packing. So in here we can consider this axis as also the time of manufacturing. If you're towards the 0, you can just complete it very fast. If you're towards here, it will take a longer time to manufacture this. And we are using this D maximum over L, which is the characteristic length, the side length for our triangle, because we want to keep things independent of the scale, so that if you increase L, you will have the same value, because the max can also increase accordingly. We can plot for different number of initiators or different number of lasers. Let's say for the 1, we have this one, and as we increase the number of initiators, we have a better and better covered area ratio, as expected. So the funny thing here is that when you just pick a covered area ratio, let's say 95% is sufficient for my application, what will happen is the best point that you can select in this time will be the smallest value that you can obtain, this covered area ratio, because the x-axis means that you have the manufacturing time. On the x-axis, if you're less, it's better. And again, as I said, there will be a sweet spot for the best area coverage for the maximum. So it is good to make an optimization here. So in conclusion, today I'll talk about the proof of concept of multi-point initiation and how can we do this in growth printing to obtain any shape that you like. We talk about the optimization that we have done for area and time of the coverage, and any shape could be created for this area in theory, and we are currently focused on the 2D. And our purpose in the future is to create some manufacturing, hopefully the same exact replicate of the simulation with using lasers. And in the future, if we can come up with a good plan for the physics, we can do the initiation beneath the surface. If we will just achieve this means that we can just create a sphere packing where we could just obtain any 3D printed shape that we would like to have in a very short amount of time. So I would like to thank to my collaborators in the AMS group at Beckman Institute, and last but not least, my Professor Vardef Ha. Thank you for listening. You can scan this QR code and reach to me via this email.